Hello, and welcome back again to the course on thermodynamics. We are still on Unit 4, the unit on the second law of thermodynamics. So we have now discussed about heat engines in the first lessons and about the refrigerators. So we have calculated their uh, efficiencies for heat engines and the coefficient of performance for a refrigerator. So in this lesson, we will now be trying to describe the ideal, the perfect engine and the ideal refrigerator, or the ones with the highest possible theoretical efficiency and highest possible coefficient of performance. And these engines and refrigerators obey the Carnot cycle. Hence, they are called Carnot engines and Carnot refrigerators. So a Carnot engine is just an idealized engine. It's an ideal engine. It's a perfect engine. It doesn't exist in reality, but it's the engine with the maximum possible uh, thermal efficiency. And this was designed by Sadie Carnot. So I think Sadie Carnot is some French. So this is the diagram of a heat engine. So the heat engine absorbs heat from a hot temperature reservoir, converts some of that heat into work, and then dumps some of that heat into a cold temperature region. So in a Carnot engine actually avoids irreversible processes and only includes reversible processes during the Carnot cycle, the engine cycle, the four-stroke cycle. So in this case, if you only take into account reversible processes, efficiency then only depends on the temperatures of the hot and cold reservoirs. So efficiency can be then for a Carnot engine is given by this. It's still a heat engine. It's still the work done by the engine over the heat input or heat absorbed by the engine, but it will now just be also equal to 1 minus the temperature of the cold reservoir over the temperature of the hot reservoir, or TH minus TC over TH. So from this equation alone, we can see that in order to maximize the efficiency of a Carnot engine, you just have to maximize this difference, the difference between TH and TC. So if the difference between the hot region and the cold region is very large, then you will have a very efficient or high efficiency Carnot engine. So it is the maximum possible a Carnot engine again is a heat engine with the highest or the maximum possible efficiency. So basically this is our guide on how to make a real engine. So if you want to make a real engine, you can follow the advice of Carnot, in which you have to make the temperature difference between the hot and the cold regions to be as large as possible. Okay. So maximum efficiency for maximum temperature difference of the reservoir. So this is now the Carnot cycle. So this is a reversible cyclic process. So reversible meaning if you reverse the process, if you reverse the arrows here, instead from A to B, you will have B to A, then you will now have a Carnot refrigerator. That's what it means by reversible process. One way is a heat engine, the other way is a refrigerator. So here you have number one, from A to B is isothermal expansion. And then from B to C is adiabatic expansion. From C to D is isothermal compression. So it releases heat in this process. It absorbs heat from A to B in the isothermal expansion. And then from D to A, adiabatic compression. So in the adiabatic process, again, no heat is involved. Now, this is the Carnot cycle for a Carnot engine. But if you have a refrigerator, a Carnot refrigerator, it will just operate in reverse. So instead from D to A, you have from A to D, or sorry, we'll start with isothermal compression first. So you have D to C, C to B, B to A, and A to D. So the reverse is a refrigerator. This process is an engine. Okay. So in the refrigerator stage, the heat involved is also reversed. So in a refrigerator in D to C, the heat is absorbed from the cold temperature region, and the heat is released to the high temperature region. It's reversed. So that's one. That's just the difference. It's the same cycle, but different directions for the arrows. So you need to change the direction of QH arrow here and the QC arrow here for a refrigerator. Okay. So the reverse cycle for a Carnot engine is a Carnot refrigerator. Okay. So a Carnot refrigerator again is a Carnot engine operating in reverse. It's still a refrigerator. So, but it has the maximum possible coefficient of performance K. And again, similar with the Carnot engine, its coefficient of performance only depends on the temperature inside and outside the refrigerator, the temperature of the cold region and the temperature of the hot region. So it's just Tc over Th minus Tc. And in contrast to the efficiency of a Carnot engine, wherein if you maximize the temperature difference between Th and Tc, you will get a higher efficiency engine. But for a refrigerator, for a Carnot refrigerator, you will have a large Carnot coefficient of performance if Th minus Tc is minimum. This is inversely proportional. So the lower the Th minus Tc, the higher the K, the higher the coefficient of performance. So for a perfect refrigerator, the difference between the hot and cold region must be very, very small, must be minimum, so that you will have a very efficient refrigerator. So this can serve as a guide. The Carnot refrigerator actually serves as a guide for real refrigerators. So real refrigerators tries to make or construct the refrigerators or air conditioners in such a way that the temperatures of the two reservoirs or the two regions are very close to each other. So let's have an example of a Carnot engine and a refrigerator. So you have a Carnot engine. It takes 2000 joules of heat from a reservoir at 5000 Kelvin, does some work, and discards some heat to a reservoir at 350 Kelvin. So the higher temperature is 500 Kelvin. The lower temperature, the colder region, is 350 Kelvin. So how much work does it do? How much heat is discarded? And what is the efficiency? So that's for letter A. For letter B, if the cycle is reversed, so it becomes a refrigerator absorbing heat from the cold region. How much work is done, how much heat is discarded, and what is the coefficient of performance? So let's first answer letter A. So the first question is how much work, how much heat is discarded, how much heat is discarded is QH, how much work is W, and what is the efficiency? So we can actually solve for the efficiency first because we are given with the temperatures. And we know that for a Carnot engine, it only depends on the temperatures of the reservoirs, the cold region and the hot region. So Tc here is 350 Kelvin, Th is 500 Kelvin, and you will get an efficiency of 0.30 or 30%. Okay, so we now know the efficiency of our engine. So what is now we can now then solve for the work. Since we now know the efficiency, we now know the heat input, the heat absorbed by your engine. It's 2000 joules of heat absorbed from the hot region. We can now solve for the work. So the work is just E times QH, and you will get 0.3 times 2000 joules. So you will get a work of 600 joules. So it absorbs 2000 joules of heat, and according to the second law of thermodynamics, you cannot convert that totally into work. So only partial of the heat absorbed will be converted into work. So actually in this case, it's only 600 joules. 600 joules from the 2000 joules absorbed is converted into work. And of course, the remaining 2000 minus 600, that will be your heat discarded, the heat released to the colder region. So you will get negative 1400 joules. So again, the negative sign implies that heat is released by the engine. Now for letter B, the cycle is reversed. So first, again, we can find the coefficient of performance first, because we know the temperatures of the lower temperature region and the higher temperature region, TC and TH. So using this formula, we can solve for the coefficient of performance. It's 2.33. So using the coefficient of performance and knowing that we absorb 2000 joules of heat from a lower, take note ha, this 2000 joules of heat will now be coming from the 350 Kelvin region, because this is now a Carnot refrigerator. So QC is 2000 joules. We have K, so we can now solve for the work. So we're not using the formula with the absolute signs here, no, because we need to find the actual work. So work is negative QC over K, and you will get negative 858 joules. And again, you expect a negative work done on the refrigerator, because this is not work done by the refrigerator. This is energy supplied to the refrigerator. The energy is the one accepting this refrigerator. So it's a negative work. So the refrigerator is actually not the one doing work, but it's an outside device that's doing work on the refrigerator. So it's negative. So work is done on the refrigerator. And to solve for the heat released to the hot temperature region, so QH, so it's just work minus QC, and of course work is negative, Q is positive, so you will get a negative result because this is heat release to the hotter temperature region. Again, this is a refrigerator, so heat is released to the hotter temperature region. So that is it for Carnot engines and Carnot refrigerators. Now in the last this is the second to the last topic of this unit, but in the last topic of the unit, we will be trying to merge the concepts of how does the second law of thermodynamics come in when you have Carnot engines and Carnot refrigerators. So basically, the next lesson will be the last lesson for this course. It will be the finale for this course. I will see you again in the last lesson for this course.